I'm Daniel Millstone. Oleg Golikoff. JJ Katz is studying for a test.
As you can see, magnification changes with respect to pupil location. This magnification causes different spot sizes. So at the paraxial focus we have this spot size, at the marginal focus we have this spot size. The distance between here and here is our maximum rate error. If we look at it from the XZ perspective, the exact same setup looks like this. So all the rays converge to one single spot, which means there's virtually no coma.
For our tangential coma, we have this quadratic relationship between our pupil location and our ray error. If we were to do this for different field heights, we would have a linear relationship for the field height. If we look at our sagittal, it's just equal to 0, as previously explained.
Astigmatism occurs when your tangential and sagittal rays focus at a different spot along the direction of propagation. If we put our viewing screen at the tangential focus, we see a line. This is because our tangential rays focus to a spot, and we're left with our sagittal rays. If we move along the direction of propagation, we see this medial circle. At the sagittal focus, our sagittal rays come to a focus to a spot, and we're left with our tangential rays leaving us with a vertical line.
We've chosen our coordinate system. We're only off axis when we look at the system from the YZ plane, but not from the XZ plane. That means that our tangential ray fan plot becomes linear with respect to pupil position, but quadratic with respect to field height if pupil position stays constant. Then if we look at our sagittal ray fan plot, it's just equal to 0.
If we have a perfect lens represented by this basketball, then rays in all orientations will focus to the same point. Now if we have an astigmatically aberrated lens, such as this football, then rays in different orientations, such as tangential and marginal, will focus to different points. We have different field angle inputs, which produce different optical powers, creating a curved image plane. Now this can be solved with defocus at different heights, or with a curve detector. Here are the ray fan plots for field curvature, which are linear with respect to pupil location, but quadratic with respect to field height. Here we have our expanded beam bouncing off this mirror and going through the Hartmann disc, and what we're doing is we have this set at the marginal focus so that all 5 of the marginal rays and the center chief ray are interfering, and we're getting this cool interference pattern here where all of the what seems to be plane waves are interfering and creating this.
After creating our off-axis field, we covered up all of the holes in this Hartmann disc except for the center one. We then moved the microscope in the y-axis and marked the position in which the spot centered over the crosshairs. That found this position right here. Then we covered up all of the holes except for the top one. That meant that we found the position in which this ray centered on the crosshairs to find the top of this marginal focus spot. We then did it for the bottom hole, which found the bottom spot of this marginal focus. That gave us all we needed to find the ray error and calculate for the coma in the tangential case. So we covered up all of the apertures except for the leftmost. Then we moved the microscope in the Y direction in order to center the spot on the crosshairs. We then covered up all of them except for the rightmost aperture. We did not need to move the microscope again because it was already centered on the crosshairs due to the symmetry of the system. Covered up all of the holes except for these 2 red ones. In the YZ plane, you can see that these red rays were the ones that made it through these red holes, and they focused to somewhere right around here. So we moved the microscope in the YZ directions until just the tip of when these 2 rays intersected was focused on the center of the crosshair. Then we covered up all of the holes except for these 2 green ones, which you can see in the XZ plane would focus onto the image plane, and the YZ plane would focus to right about at this dot. We moved the microscope in the Y and Z directions to focus this green dot on the center of the crosshairs.
Here are the Zmax plots of our ray error. Here we can see for 0 field height that there's clearly spherical aberration. As we go to a higher field height, we see that there is a linearly induced astigmatism and field of curvature. There's also coma, which you can see based on the offset of the curve based on this comparison with this field height, and this field height here is offset slightly. As we scroll down, we see that there's clearly coma in this spot. Scrolling down further, we can see field curvature is clearly present at the different field heights. Here, here, and here, it slowly curves. Compared to our Zmax data where we were plotting pupil height, here in the lab we are plotting field height. For coma, there's a linear relationship based on H value within the ray error. This was shown to be true in the tangential case, and for the sagittal case, it was supposed to be 0, which is about what we found in the lab. For astigmatism, the field height has a squared relationship based on the H squared value, which we saw in the tangential case. For the sagittal case, it was meant to be 0.